broken down in our bodies to provide energy for growth and function. A general overall equation for this very complex process represents the degradation of glucose to carbon dioxide and water. And if 856 grams of glucose is consumed by a person over a certain period, what's the mass of carbon dioxide produced? Do I have? Nope. Okay. Thought maybe I had extra space. So, what were the numbers? What color of ink should I use first?
Purple.
Oh, I heard purple first.
Yellow.
So our equation was C6H12O6, right? Is it balanced? No. How would we balance it first?
Write down what each time.
So we have 6 C's, and O we have 8. We have 3. Now what? 6 here, so that means changes this to 6, and that changes that to 13. And a 6 here, I heard? Changes that to 12. And now we have 12 plus 6 is 18? No, I don't want 9. Yeah, because then I'll have 12 plus 6 is 18 as well. Okay, now we're balanced. And it says we have 856 grams of glucose, right? And what is it asking for? How much carbon dioxide? So we always start with what's given. So we know we have how much glucose? We have 856 grams of glucose. And in order to convert from one compound to another, we need to be in the moles units. Our units need to be moles because that would be equal number of atoms. We'd have equal number of atoms that we'd be comparing then. And so we need to convert this into moles by doing what? What do we put on the bottom? Molar mass, and so it'd be 6 times 1001, oops, 1 times 6 plus 12 times 1.01 plus 6 times 16. 180 even? Close enough, or what is it? I think it is 180 something. 0.01? 0.18? And that's the mass of 1 mole of. So this is where we're going to convert from glucose to carbon dioxide. And so for every mole, every molecule of glucose, how many molecules of carbon dioxide do we get? 6. So for every mole of glucose, how many moles of carbon dioxide do we get? 6, right? Because they're equal amounts of atoms or molecules. So for every 1 mole of glucose, we get 6 moles of carbon dioxide. I guess we haven't been canceling. Let's show our cancel units canceling. And does it ask for moles or grams? Mass. Okay, so we aren't quite finished yet. We need to change moles into grams then. So 1 mole of carbon dioxide was what's the mass? Two times 16 is 32, 44.01. Right, 32 plus 12, yeah. And that's CO2. So this is where it's good to include what molecule you're using, because you want to make sure the right numbers. You wouldn't want to have a 1/6 ratio here. You need to make sure it's 6/1, so it's good to use your formulas. And what is the answer you get here? Take 856 times 6 times 44.01, and then divide by 180.18. And point what? 497, so let's go 50. Do we have people who agree? Did that calculation and got the same? Okay. So questions on any of those steps? Okay, let's try another one. Now all alkali metals react with water to produce hydrogen gas and the corresponding alkali metal hydroxide. So here's the reaction with lithium and water. Is that equation balanced? You should always check that first.
Yes.
Yep, 2 lithiums, 4 hydrogens, and 2 oxygens on each side. So how many grams of lithium? So this time we're looking for how many grams of lithium are needed to produce 9.89 grams of hydrogen gas. So it doesn't matter if we are giving the amount of reactant or product, you're still going to do the same process. It doesn't even matter if you're looking at, okay, if I produced 9.89 grams of hydrogen, how much lithium hydroxide would I also produce? It doesn't matter which compound you're converting to, you do the same process. So how much hydrogen gas do we have? Right, so we start with the 9.89 grams. And our first step is to convert to moles. So what's the mass of 1 mole of hydrogen gas? 2.02. Does everyone see why we got? It's H2, so we have to take 2 times 1.01. Now what unit needs to go on the bottom? Moles of H2. And we are converting into moles of lithium, right? Once we're in moles, we can convert from one compound to another. And what numbers are we going to use here? For every 1 mole of hydrogen gas that we produce, how many moles of lithium does it take? 2. So for every 1 mole of hydrogen gas we produce requires 2 moles of lithium. We'll use our coefficients. Moles of hydrogen then cancel. And it is asking for grams. If it asks for moles, we could just stop there. But we need to convert this back into grams. So 1 mole of lithium, 6.94. These cancel. So you take 9.89 times 2 times 6.94 and then divide by 2.02. And how much lithium do you get? 67.96? So the conversion steps really are the same. The most important thing you need to remember is in order to convert from one compound to another, your units have to be moles, because that means you're comparing equal amounts of compound. Okay, let's see what we have next. Okay, limiting reagents. So usually in a reaction, you have a limiting reactant and you have a excess reactant. Now, reactants and reagents, they're interchangeable. They mean the same thing. I usually use the reactant. So the limiting reactant is the reactant that would be used up first. It's limiting the amount of product, because once that reactant is used up, the reaction stops and you can't produce any more product. So it's limiting the amount of product that you can produce. The excess reagent then is the reagent that's left over. Once the limiting reactant is done reacting, there's still some extra of the second reactant left over, and that would be your excess, and you could calculate how much excess would be left over. An example would be, let's look at our desk and to student ratio. So let's say our reactants are the desk and students in this class, and our product would be a student in a desk. What would be today, what would be our limiting reactant? Today it would be students, right? Because we ran out of students first before we filled up all the desks, since we have some people gone. Which would be our excess? The desk would be an excess. Now, on a normal day, when everyone's here, what would be the limiting reactant? The desks, because we ran out of desks before we ran out of students. And excess would be students, yes. Same idea, we're just going to be looking at actual compounds and chemicals in their reaction. So whenever we do that calculation from amount of reactant into product, that's called a theoretical yield. And so you're going to have to calculate theoretical yields, and we'll compare them to how much we actually have. So let's go through this process. Urea is prepared by reacting ammonia with carbon dioxide. Is that equation balanced? CO2 nitrogens. Here's 6 hydrogens. There's 6 hydrogens. 1 carbon, 2 oxygens, 2 oxygens. Yep, it's balanced. Okay. In this process, 637.2 grams, so 637.2 grams of ammonia are treated with 1,142 grams of carbon dioxide. So we know the amounts of the 2 reactants. We need to figure out which one do we run out of first. That would be our limiting reactant. The way I do it, and I honestly can't remember how your book does it. But the way I do it, and if you follow and read the book and like the way the book does it, you'll get the same answer. It doesn't matter. I choose one of the reactants. So which reactant do you want to start with? The smaller one? Okay. So we have 637.2 grams of ammonia. What I do is I convert that into carbon dioxide. So if I react all of this ammonia, how much carbon dioxide do I need? How much carbon dioxide would I have in order to react all of this ammonia? Then I'm going to compare that to how much I actually have to see if I have enough. Do I have enough to react all of this ammonia? Well, we got to go through some calculation because it's not a 1-to-1 ratio and our masses aren't equal. So 1 mole of ammonia is 14.07 or 01? 01. 07 plus 3.03, 17 even? Oh, 17.1. Is it 14.01 or 14.0? Yeah, that's right. 04. Okay. And now what's our next step?
Change it from moles of
2 moles of CO2. So for every, this time for every 2 moles of ammonia, how much carbon dioxide do we need? 1. So it's a 1-to-2 ratio.
How do you figure that out?
We just use our coefficient, whatever the coefficient is. And if there's no coefficient, that means we just have one of them. And then 1 mole of CO2, what it says 44.01, right? Yeah. So if someone would calculate, now this is how much carbon dioxide we need to react all 637.2 grams of ammonia. $822.86. So if we react all of the ammonia, we need 822.86 grams of carbon dioxide. How much do we have? Over that. Do we have enough? Yeah. Yes, we have plenty. So that means carbon dioxide is excess. We have extra of the carbon dioxide, which automatically means we will run out of the ammonia first. We will run out of ammonia before we run out of carbon dioxide. So that means that which of the 2 reagents is the limiting? That would be ammonia. Does that make sense how I compared them?
Yep.
Okay. Let's skip this question and go to this question because this is asking about excess reagent. Which ones are excess? Carbon dioxide. And it's saying how much excess is left. How would we figure out how much is left? Just subtract them. 1,142 grams of carbon dioxide. Subtract 822.86 grams of carbon dioxide. Now, just to show you that it doesn't matter which one we choose first, I'm going to quick write out the conversion between and let's see what we would have gotten. Oops. Would someone calculate this real quick for me? So this is saying if I react all of that carbon dioxide, how much ammonia do I need? 834.3. So it's saying that if we reacted all of this carbon dioxide, 1,142 grams, we need 884 grams of ammonia. Do we have 884 grams? No, we only have 637. So either way, you'd still get ammonia as your limiting reactant. But if you would have started with this, not that it's bad or anything, but you don't know how much. We know that carbon dioxide is excess, but we don't know how much of it we're going to use. So you'd have to go through and do this conversion again to figure out how much carbon dioxide you use up to subtract it from this number. Does that make sense? You'll get the same answer. It doesn't matter. Now, to do the second, the urea is a product. So which reactant determines how much product is formed? The limiting or the excess? The limiting. So in order to determine how much product is formed, we should use our limiting reactant because that determines how much product. I'm going to erase all of this. We're going to start fresh. So our limiting reactant was ammonia. So we're going to start with 637.2 grams of ammonia. This is for the second, how much product the urea is formed. What was that? That was 17.04. And then 1 mole of urea. Oh, wait, not 1. We have 2. For every 2 moles of urea, or every 2 moles of ammonia, sorry, how much urea do we produce? For every 2 ammonias, we get 1 urea. I'm going to just put I'm going to call it urea instead of writing all that out. That should say 1 mole, too. Oh. Has anyone figured out the molar mass? How many nitrogens do we have? 2. And how many hydrogens? 4, plus carbon plus oxygen. I have no idea what that is. $60? Okay. I'm going to take your word. So just check our units. Everything's canceling. Good. So how much urea is formed then? $1,128.3. 21.83. Is that what everyone else got? Yep. We're trying to figure out how much, because it's asking for mass of urea. So once we got to mass of urea, we stopped. If it were to ask for moles of urea, we could stop. We wouldn't need this step because we'd be left with moles as our units. Okay. We added up the mass of this. So 2 times nitrogen, 4 times hydrogen, carbon, and oxygen. Okay. Yeah, we weren't going to do that. So your worksheet is going to be due tomorrow that you got on Wednesday? Is that the Wednesday when we got it?